Hello everyone. My name is Madhu and I'm a postdoctoral researcher at the University of Hull. At Hull, our primary focus is on the through life monitoring of offshore renewable energy structures. As part of this work and under the core research program of the Supergen ORE Hub, we are developing subsea power cable monitoring systems using distributed optical fiber sensing technologies. Subsea power cables are critical assets for offshore renewable energy systems. Failures in these cables are costly, time consuming to repair, and can even have significant impact on energy supply and system reliability. These cables may fail due to range of factors, including electrical and thermal issues. However, many failures are primarily caused by mechanical loading under production, transportation, installation, and operation. Our aim is to use standard telecom grade optical fiber to monitor large deformations in subsea power cables under both static and dynamic loading conditions. There are a few types of distributed optical fiber sensor technologies that are widely used for applications in structural health monitoring and condition monitoring. Among available optical fiber sensor technologies, Brilliant Optical Time Domain Reflectometry, called as BOTDR, is widely used for distributed static and quasi-static strain measurements. BOTDR measures absolute strain over tens of kilometers using a standard optical fiber, and it can separate strain from temperature effects without having auxiliary fibers. However, conventional Brillouin sensing has inherent limitation for dynamic measurements due to long accretion times, usually from seconds to minutes. In this study, the experimental work was conducted by using slender cylindrical structures. A single mode optical fiber was attached to the outer surface of the slender cylindrical structure in two different configurations, parallel to the axis of the cylindrical structure and in helical windings around the cylindrical structure. In order to monitor the direction of the bending, the fibers were oriented from 0 to 180 degrees around the outer surface of the cylindrical structure. And distributed strain along the structure was measured using a BOTDR. To investigate large bending deformations in slender cylindrical structures, a 6-meter long conduit with a diameter of 40 millimeter was tested under 3-point bending and constant curvature bending configurations. As mentioned earlier, the optical fibers were attached to the outer surface of the conduit. For each test case, 5 different levels of mid-span displacement or bending radius were applied, and the quasi-static strain response was measured using a BOTDR. By analyzing the strain data, it was possible to determine the magnitude, location, and direction of the bending deformation. In addition, as shown here, the measured strain responses were also used to reconstruct the shape of the bending deformation, which is important for monitoring the behavior and condition of subsea power cables throughout their service life. If you would like to learn more about these findings, please refer to the journal paper below for a more detailed understanding of the work conducted. Our ongoing research more focuses on dynamic subsea power cable monitoring. Here we use an automated dynamic flexural test rig to monitor a 3-meter long slender cylindrical structure under cyclic bending. This presents one set of experiments conducted as part of this study. 5 low-frequency dynamic displacements were applied and BOTDR data were recorded. However, dynamic loading broadens and distorts the Brion gain spectrum, affecting conventional Brion frequency shift-based measurements. In this study, we investigated the relationship between BGS spread and dynamic displacement range. Evaluating BGS features such as spectrum spread offers a practical means of estimating dynamic displacement. This demonstrates the potential of BGS derived parameters for characterizing both static and dynamic behavior of subsea power cables. Please feel free to get in touch for further discussion. I would like to welcome the opportunity to discuss this work further and explore potential collaborations at the Supergen ORE Annual Assembly. Thank you.